So we looked at unsteady laminar flow from a moving plate in an unbound, right? And we saw that led to the similarity method, the similarity solution, and those are fun. But now, what happens if we have a boundary layer? Right? How does that affect our flow? All right, and so that's what we're going to work on probably all day today, and certainly some of Monday. We're going to talk about. We'll see how far we get into this problem. I think we'll kick the homework back to Wednesday because I think the homework has two problems on separation variables. Let's not kill ourselves all weekend. You know, I think there's the two separation variable problems. So we'll kick it back to Wednesday. Okay, I'll update that. And then we'll talk about. So we'll probably get somewhere in the middle of D today. I guess maybe we'll get a little bit from it. And then we'll start talking about Sturm-Liouville problems on Monday, and hopefully we'll get through that on Monday. So basically, Sturm-Liouville problems is a sort of generalization of the example we're going to do here. And so we'll talk about how to do this when you've got space variables or different geometries, how that kind of plays out. And we won't do probably a ton of examples, but I want to give you a flavor of that so that you have a sense of it when we see it in other problems. Okay. So that's the kind of overview of where we're going. So, so part A is a problem setup, and we talked about this a little last time, but I drew it up a little nicer here. So if you want to update your notes. So we're going to think about the startup of Couette flow, right? So Couette flow is the case where you've got the parallel plates and one of them is moving. I think that we do that like the first day in undergrad fluids, and we keep coming back to it, okay? And now we're going to consider the transient case, okay? And so we need to think about what the governing equations are here. So fortunately, we just did an example, so we won't go back to the Navier-Stokes equation because we literally just did this like a day or two ago. And so we can just write down the diffusion equation for momentum. dvx dt is equal to nu, second derivative of vx, call it the y now, next, y squared, right? So it's the same equation that we had. The only thing that's going to be different here are the initial and boundary conditions. So the boundary conditions are going to be Vx at 0 in the y direction p, that's going to equal V naught, and Vx at Vt is going to equal 0. And then the initial condition is Vx at y time equals 0 is equal to 0. Okay, so these look almost exactly the same as from before, but this is at p, whereas last time it was at infinity. Okay, and so we're going to see that this makes a drastic difference in the solution method, which is kind of interesting, right? That the last time we only had an infinity here, and we did the one thing, and we're going to do this with a geometry that's different and changes the whole problem. Okay, so that's kind of interesting. It's also kind of useful to, I'm going to just write up here, what are the equivalent heat and mass transfer problems for this? So it's the same kind of thing we had last time. So for mass transfer, it will look like dCA dt is equal to dAB, the diffusivity, second derivative of concentration with respect to y squared, with similar boundary conditions. CA at 0 is CA naught, CA at B, comma, T is equal to 0, and CA at Y, comma, 0 is equal to 0. So that would be the concentration. And I'm going to write this one a little different because we got pointed out last time that we have to move the temperature around. So we'll call this a theta. And we'll make this a second derivative with respect to Y with theta, where theta is going to be T minus the ambient temperature, okay, the sort of temperature that already exists in that space, okay, so that'll just be the temperature difference. And then what we'll say is that theta at 0 t is equal to theta naught, which is equal to t naught minus ta. Okay, and that takes care of that little issue we had last time with the temperature being not 0. So b t equals 0 and theta at y comma 0. Okay, so we're going to simultaneously solve all these problems. Okay, so you could basically go back and work through it if you wanted and plug in the different variables and get out the solution. Okay, any questions about the problem set? Make sense? Okay, so B, we'll do non-dimensional. Okay, so in this case, the dimensional analysis is going to be easier, okay, because we've got our length scale here, and that's going to allow us to, basically what it's going to allow us to do is get rid of these parameters, v naught and nu, and we'll get ones in those spots. So let's show how to do that. So we're going to define a phi equal to Vx divided by V naught. That's the same thing we did last time. And this time I'm going to define a y tilde is equal to y divided by b. Okay, so now I have that length scale. Phew, that's happy. And then I'm going to take t, I'm going to make that divided by a time scale. And this time, for this time scale tau, I'm going to use I'll make tau b squared over nu. Remember, nu is the kinematic viscosity, has a length, or it has a units of length squared per time. So if I do that, I get a time. So I'll put that in here, and I should get what, t nu divided by b squared. I could write nu. Okay. So we can take this and plug it into here and here, and we should get out an alternate, a non-dimensionalized set of equations. So we'll do that over here. I'll put let's see, Vx will become theta or phi v naught, and then dt becomes t tilde, and I'm going to have b squared over nu. Is that right? Yep. And then over here I have a nu and a second derivative with respect to, let's see, second derivative of Vx, which will be phi naught. On the bottom, I'm going to have y tilde b squared. So now I pull that stuff out and have a v naught divided by b squared, nu on the top, d phi dt tilde. And I have a nu v naught divided by b squared, the second derivative of v with respect to y tilde. Okay, that's the same coefficients out front. So that's why I picked it. And that goes away. Okay. So I could have picked a different time scale. I could have picked the time scale of this right here, this v naught, right? But then that would have given me a ratio here of some constant that would have stayed fixed, and it would have just been some number. But this one nicer, okay? Because what we're interested in is that diffusive time scale, right? Of how long it takes to diffuse it. So that's the better time scale to pick. So we end up with that. So then the last thing we need to do is fix our boundary conditions. And this is really easy. We just divide by v naught on both sides, right? And we're going to get phi at 0 t tilde is equal to 1. And phi, and then we're going to divide that b, right? We're going to put it in a y tilde. So that's going to become a 1, comma t tilde is equal to 0. And phi at y tilde comma 0 is equal to 0. And I'll rewrite that guy since it's kind of ugly. T tilde is equal to the second derivative of So what's nice about this now is that we can just solve this problem with the one there and the one there, okay? And we don't have to worry about carrying around all the news and stuff. And if you did a dimensional analysis on this problem and this problem, if we wanted to do that, we'd end up with this exact same math problem, okay? So the kind of nice thing is that we just reduce this to a math problem, and then we can solve the math, and then we can go back to thinking about it physically. This is one of the things I really like about non-dimensionalization. Not only does it do things like give us insight into similarity problems, but it allows us to basically go from this to a math problem. And in my mind, like when I'm thinking about solving a problem, there's sort of the physical setup, and then I think about the equations, and then at some point I need to get it to where I'm going to do math, right? And so to me, I like that it's this clean process of like, I do the problem, and then I turn it into math, and then once it's math, it's just math, right? So if I wanted to solve this on a computer, that's easy. I don't have to worry about units, I don't have to worry about anything, right? I just solve it, okay? Solve the math problem just like I did in math class. Then once I have the solution, now I go back, use the non-dimensionalization, turn it back into something that makes sense, right? But I know that this has like the most general applicability or whatever. So anyway, that's kind of as a theoretician, that's what I like to do. Because when I have to flex my math muscles, I don't want to mess around with my units muscles because those aren't as strong. So, all right, questions on that? Hopefully that was pretty straightforward. Okay, all right, let's see, that was B, let's do C next. Got my garbage marker today, that's hard to erase, trying to use it up so that I never take one of them again. What brand is it? It's thick. Good at pens, bad at markers. There, it sounds like I'm the salesman for the other brand. Thick. Bad for markers, you know, or what political ad, right? Don't vote for Bic. We're gonna find out today, you think? You don't think so?
It's going to be like, I think it's at least a week before it's official.
The National Guard rolls in, throws lasso around Trump and pulls him out. Is that how long it is? Let's hope it doesn't come to that.
Oh, that'd be kind of fun to watch.
That
Picture point where that has to happen. That'd be cool. I'm not gonna lie.
what we should do is have a reality show where someone tells Trump, "You're fired," right? Like that's what we should do. Anyway, I don't know. Maybe you guys like Trump, so I'm not trying to bash on him. I just think that would be kind of funny to watch. It's ironic, really. All right, I guess I could rewrite this. Oh, it took me an hour to erase. My hand's a little tired now. Only for an engineering professor would that be a workout. I played so good at basketball on Wednesday, and I knew today wasn't going to be as good, but still a little. I hit 3 game winners on Wednesday. I mean, how can you beat that, ChEn? You can't beat that. 3 game winners out of 4 games. Like, that's pretty good. So they were all 3-pointers. The last one was pretty fun. Came off a pick, came around, caught the ball, shot it. I felt like, you know, Steph Curry for about 6 seconds. Then I realized that I'm not. Anyway, it's fun. Okay, just dribbled off. We didn't talk about it. Scored that. It's kind of fun. I meant to do that right off my leg. That was how I planned it. Tim came to basketball. You guys know Tim? The senior. Anyway, if you want to come to basketball, come play. Come block Tommy. Don't go to me. Okay. All right. So unlike in the semi-infinite domain, okay, back to separation of groups. In the semi-infinite domain, there's no top boundary. So there was never a steady state solution, right? That's what's kind of interesting about that problem. So you have to solve the unsteady version. But we know in the parallel plate there's a steady solution, right? We know that happens because we solved that one like forever ago. So let's just remind ourselves of that steady state solution, okay? So there is a steady state solution. Okay, so we're going to let phi infinity equal phi at y at infinity, or i.e. t, let's see, the limit as t approaches infinity of phi of y t. Okay, steady state solution. Okay, so we know in that case that we're going to get d squared phi infinity dy squared equals 0. Right? So if we remind ourselves maybe of our problem, it was d t y, no, dy dt. Goodness. It must be Friday. What are you talking about? Why? There's a phi. If you're going to correct me right. Okay.
I told you.
She's on a high because her paper disconnects. All right, here we go. So that was our solution. We're going to say that at infinity we get this. And for the rest of this, the lecture, I'm not going to put tildes on the t and the y. Okay. So we did the non-dimensionalization, and I'm just going to drop the tildes because it's a pain. Okay. And so I'm allowed to do that, so I'm gonna. Okay. Because I make the rules. All right. That's for today. Okay. So then we have the other one. We have the boundary condition phi infinity at 0 equals 1, and phi infinity at 1 equals 0. And that came from, we had phi at, what was it, 0 comma t is equal to 1, phi at 1 comma t was equal to 0, and we had the initial condition phi at y comma 0 equals 0. Okay, so we're going to solve this guy. Okay, well, we know that guy. The answer is phi infinity is equal to C1 y plus C2. Right? We've solved that lots of times. We just need to apply the boundary conditions to make sure we get the minus signs right, figure it all out. So phi infinity at 0 equals 1. Well, when I put that phi infinity at 0, that gives me C2. So C2 equals 1. That's happy. Okay. If I come over here, I have phi infinity at 1, which is going to be C1 minus or plus 1, right, is equal to 0. So that means C1 is equal to minus 1, and I get phi infinity is equal to 1 minus y. Okay. So that's just my Couette flow solution, right? So I have 1 at the bottom and then minus y, right? So I've got the linear flow profile. I can see that, right? Looks like that. And that crosses that point. Okay, that's the steady state solution. And what we want to do is we want to use this steady state solution and subtract it from our solution here to get a transient solution. Okay, so we want to isolate just the transient part. Okay, and we're going to see that what that's going to do is it's going to make our boundary condition that's going to change up. Okay, and we'll talk about this probably next time, but to do separation of variables, you want homogeneous boundary conditions. So if you remember, homogeneous boundary condition is a boundary condition equal to 0. Okay, and so we want these to be 0. So what we want to do is use the fact that we know what the phi infinity is, okay, to change this problem a little bit, to change up these boundary conditions a little bit, right? Because we don't want to have to solve it with the 1. So that's what we're going to do here. So we want to have homogeneous boundary conditions for separation of variables. So we do the following. Okay, we define to phi t at y t is equal to, and I'm doing this in my head, we're going to make it, well, we're just going to write about how I do it. We're going to define the following: phi infinity at y minus phi t at y. We're going to make our total solution equals this, and that's really just defining this piece, okay? We know that, an equation for that, we know that, we just solved for it, okay? And we want to say, we're going to find phi of t. That's going to be the thing that has when we're doing this boundary conditions. I think it's a little funky because we're subtracting phi infinity minus the phi, essentially. So it's maybe negative what you might think. I don't know why. Maybe that makes the boundary condition positive for this, which is what we're going to do here. Okay, so let's plug that in and think about what happens. So we need to plug that definition of this right here into our original equation and into our boundary conditions and see how it transforms. Okay, so we're going to do e of phi infinity minus phi t is equal to second derivative with respect to y of phi infinity minus phi. Okay, so well, we know that the time derivative of this is 0, right? Because that's what we assumed when we said it was steady state. Okay, and then we know that the second derivative is equal to 0 because we set it equal to 0 right there, right? So this one doesn't matter, goes away. Okay, and so we're going to get d phi t dt is equal to second derivative of phi t dy squared. Okay, so same PDE. That's good. We wanted to keep the same one. What's up? Oh, never mind. Yeah, and there's a minus signs that cancel on both sides. Okay, then what we got to do is the boundary conditions and initial condition. Okay, and so here we're going to put we have phi at 0 comma t is equal to 1. That's this one right here. So we're going to make that one phi infinity at 0 minus t at 0 comma t. Right, so that's just plugging in the definition into the boundary condition. Well, we had phi infinity at 0. Phi infinity at 0 is 1. Okay, so that's going to equal 1 minus phi t at 0 comma t. Okay, and the ones cancel, and so now I get phi t at 0 comma t is equal to 0. Okay, well, that's one of the boundary conditions. That's the one we were worried about, by the way. So that makes our life easier. The next one is phi at what, 1 comma t, is that right? 1 comma t is equal to phi infinity at 1 minus phi t at 1 comma t. Okay, and we saw that one equals 0, and that one also equals 0, right? So we get phi t at 1 comma t equals 0. Okay, so those are the homogeneous boundary conditions. So that makes us feel happy for separation of variables. Now we need to do the initial condition. The initial condition is phi at y comma 0 equals 0. That one's going to equal phi infinity at, or let's see. The initial condition, we don't have initial condition for phi infinity, right? I just left it like that. Minus phi t at y comma 0. Oh, okay. So this is the important point. So phi infinity, right? That one is it's the same all the time. So that needs to stay in there as our answer because we're not evaluating it any time. So what we're going to say then, since that equals 0, is that phi t at y comma 0 now equals phi infinity. Okay, which in this case is going to equal 1 minus y. All right. So what we did was we changed from a case where we had a really simple initial condition, but a non-homogeneous boundary condition, and we changed the problem to have a really simple set of boundary conditions and a little bit more complicated of an initial condition. All right, and you don't know why if you don't know separation of variables. You don't know why that's important yet, but it's important. Okay, and so we're setting it up. This is our last step of setup. Now we're going to get into separation of variables. Okay, and I'll tell you why when we get there, why we need to have homogeneous boundary conditions, and why it won't matter that our initial conditions will more complicated. Okay, so we're at 9:30. So got 20 minutes. Questions about this? Okay, I see some brow furrowing, which I expect that's thinking. I'm happy with brow furrowing. That makes me wonder if there's questions. Yes.
What is the X feature there? Is that just a
X. This? Oh, this was a 1 and I canceled.
okay?
But I was lazy because I didn't want to write another step. So I canceled across steps.
That's confusing.
Okay, yeah. Sometimes I get lazy on that. You good, Brian? Yeah. Okay. All right. Should we do separation of variables? Should we go? Okay. Yes, this is the best one. Okay. Now, fun fact, when you come to interview for a professor job at BYU, they make you teach a lecture to see if you're going to be good enough for you guys. And at the time I came, they let you pick what thing you were going to lecture on. And I had just given a lecture on separation of variables at Santa Barbara as a substitute for my postdoc advisor who's traveling. So I came and I took my lecture and kind of screwed it up, and I came to give separation of variables lecture. They said I could give whatever I wanted, and I figured it's like a good topic, right? And it's a transporty thing. And so anyway, I gave a lecture on that. Well, what they didn't tell me was that they weren't going to give me a full 50 minutes. They told me I had to do it in 30 minutes. But they didn't tell me that until I was sitting in the seat about to come up. So I'm at a job interview, right? And I prepared the separation of variables. And then they told me right then, like, by the way, you know, like you got till 9:30, you know, or whatever it was, like it was like 11. I think because they do it at lunchtime, they give all the students pizza. Maybe some of you were there, I don't know. But anyway, it's long enough ago, okay? And so they said, you know, Dr. Baxter goes, oh, and you've got till, you know, 12:30, so go ahead. And I was like, 12:30? Yeah, I'm like, now? So I had to like on the fly, like taking my notes and changing the lecture. And at the end, they were like, you were going a little fast. I don't know, you kind of snowed the students over with separation of variables. What do you want from me? Anyway, so, all right. All right, so we got so that was my story about this lecture. So we'll see if I do you guys. Okay, so we've got our equation, we've got our boundary conditions. So there are 5 steps to separation of variables. It's long. All right, there's 5 steps. So the first step is this one. So step 1. This marker's running out. Yes. Assume the full form. Form has an M in it, or an R in it, rather. Form of, I'll just say this, product solution. Okay, so the step 1 is assume a product solution. We're going to try the underhand technique. Oh, it's too long that time. It's the first time I've been too long. Always been short. What does that mean, a product solution? That means I'm going to have phi t is equal to f of y multiplied by g of t. Right? So I'm going to assume that my problem can be separated into a function of y and a function of t. That's separation of variables. So unlike the other one where we had to find out about the name at the very end, this one makes sense at the beginning, right? Separation of variables. Okay, so we don't have at this point, there's no justification for this. There's no like good reason. We're just postulating. And as you know, in solving differential equations, this is often how it works, right? You spend a couple hundred years trying a bunch of different things. One of them works, then you get the solution named after it, right? So Fourier, I think, was one of the first people to do this. I don't know who all the people were, but you guess. Eventually works out. That's why like every differential equation like that isn't linear is named after someone, right? It's like the Blasius equation and Chebyshev's equation and you know all these other equations, right? That's because every one of them was solved by like a different person right, over the years. And then, anyway, so that's kind of fun. All right, so what we do now is we take this product solution and we plug it back into our differential equation. Okay, so time derivative of f of y g of t is equal to the space derivative. I want to do x, but it's y. Of f of y g of t. Okay, and what's really nice about this guy is that on this side, this thing doesn't depend on t, and on this side, this guy doesn't depend on y, so they can come out. So I can have f dg dt is equal to g second derivative of f with respect to y. Okay? All right, and then I can do another step and I say, let me gather like terms. So I'm going to put g over here and f over here. So if I do that, I get 1 over g dg dt is equal to 1 over f, second derivative of f with respect to y. Okay? So I have now totally separated the variables, okay? And that's the end of step 1. Okay? Questions about step 1? We good? Makes sense. Pretty simple. I think the key to this other random markers is that if you get it early enough, it's easy to erase. But if you leave it for like 20 minutes, it's harder to erase. I'll erase it. Okay, step 2. Okay, in step 2, we are going to set this equal to a constant. Okay, so in this step, I just said that I separated these variables. That means that I know that this guy over here is only a function of t, and this guy over here is only a function of y. And the only way that they can be equal is if they're equal to a constant. We used that same principle back when we did Poisson flow. Do you remember that? Where we had the pressure derivative with respect to one thing, and the other, the viscous term that was y. And so this one's dp dx, that one's dvx dy. They have to be equal to a constant. Okay. So we've used that concept before, but do you buy this? Can I do that? Does that make sense? We're all good with that? Okay. So if I set that equal to a constant, that also means that those are total derivatives. Okay. And so what I've done is I say 1 over g dt is equal to some constant. And I'm going to make it minus c squared. Okay. My constant. Okay, I pick. Whatever I want. I'm going to call it minus c squared. Why do I say minus c squared? The reason I want it to, I make it square, or one reason is that if I say that, that means that's positive. Okay, and then I put a negative sign on it, so it means it's negative. And what we'll see is this is going to relate to an eigenvalue problem, okay, that I'm going to solve for the other piece. Okay, but we're not going to talk about that in detail until we talk about Sturm Liouville. Okay, but that's where this is coming from. So what I'm essentially doing is picking the sign of the eigenvalue by setting. Okay, it also works out because I take square roots of something, that ends up being nice. All right, the other thing I then have is 1 over f d squared f dy squared is equal to minus c squared. Okay, so that step is maybe the easiest step, okay? But I think there's other a lot longer steps, but I wanted to highlight it. Oh, got this twice here today. Step Okay. Solve the time dependent. Okay, so what we've done is we've taken what we've done, here by the product solution. What's genius about it is it turns an ODE that we can't solve, or excuse me, a PDE that we can't solve into two ODEs. Okay, so what we're going to do in the next two steps is solve the ODE. So the first one we should do is the time dependent one, because it's the easiest one. So let's do that one. So we've got 1 over g dg dt is equal to minus c squared. Okay, we know how to solve this guy, right? We've got log g is equal to minus c squared t. Okay, that seems pretty good. And that means that we're going to get g is equal to some constant, what do I call it? A exponential minus c squared t. Okay, and then this is not known yet. Arbitrary. What is the integral? What do you need a second constant? That's the second constant. Oh, good. Okay. Okay, so that a right there, that's the second constant. So I could, for instance, like get a, plus c out here, plus a prime or something. Okay, and then when I take the exponential, I take e to the a prime is equal to a. So. Okay. Right. So that's all of step 3, believe it or not. Okay, and we are not going to evaluate a yet. That is the last step. It's the hardest step. Okay, let's find a. Okay, step 4. Solve the space dependent. See how far we get this. Okay, this one is always a boundary value problem. Okay, so that's one thing to remember for the future. It's always the boundary value problem, and this is going to be also sort of key to the future. This is going to be the eigenvalue problem. Okay, if I write it up, maybe you'll be able to see that. So I can write this as d2f dy squared plus c squared f equals 0. Okay, so kind of the hint, if I call this an operator, I could call this LF plus CF equals 0, c squared f equals 0. Right, this was a matrix, right? That looks a lot like an eigenvalue. So this L, which is a linear operator, is going to be an eigenvalue problem. Same thing, right? Anyway, that's just kind of preview over the theory. Okay, so this is, if we look at this, this is a second order homogeneous. What else? Linear. Any boundary value problem. And so the solution is well known, right? So which one is this one? You guys remember? Who remembers ODEs? Look at me. There's 2 guesses, right? There's sines and cosines or exponentials. And we have second order linear ODEs. Which one? Sines and cosines, okay? Isn't that all based on the sign of this guy, right? So this one's sines and cosines. So I get f of y is equal to b sine of cy plus big C cosine of little cy. The fact that I've got a big C and a little c, kind of annoying, but it's not going to matter because big C is going to be 0. So it's going to go away real quick. Okay, so that's the solution to that ODE. So now I need to apply the boundary conditions. All right. So the next step is apply the boundary conditions. Okay. So I have a little bit of a problem before I apply the boundary conditions, and that I wrote down the boundary conditions for P, but I didn't write down boundary conditions for F of G, right? So how do I do that? Turns out it's not that big of a deal, because if I write down P at 0t, which I said was equal to 0, this is the same as F of 0, G of t. Well, if G can be anything as a function of t, right? Then that means F of 0 has to be 0, right? So that's not too bad. Okay, and the same game over here. If I have P of 1 of t is equal to 0, now I get F of 1 G of t. Okay, now I get F1 equals 0. Okay, and so it turns out, so this is why we needed homogeneous boundary conditions, by the way. Okay, because if these conditions are functions of something or whatever, then I don't have this property that that's equal to 0. Okay, and I can't say immediately that that's 0 and that's 0. Does that make sense? So I needed that to be homogeneous for that to work out in this step. And that's just because I already know the answer from the beginning how to do this, but I knew that I had to have homogeneous boundary conditions to do that. Okay? So that's why we did the whole find the steady state solution and subtract it. Okay, so now we can apply those boundary conditions to this guy. So let's do that. Apply boundary conditions. Okay. So when I apply the boundary conditions, I say F at 0. Well, if I take F at 0, that means that I put a 0 in for there and a 0 in for there. Well, sine of 0 is 0, but cosine of 0 is 1, right? So I'm going to get C out of that, right? That's cosine of 0 is 1, and that's going to equal 0. So C is 0. Phew. Like I said, big C, little c, we're not going to have to worry about that anymore. Okay, let's do the other one. F at 1, if I plug in 1, now I'm going to get P sine of C, little c. Now that's equal to 0. Okay, now there's two possibilities here. Okay, the first possibility is that B is 0. If B is 0, I am wasting my time, right? Because if B is 0 and C is 0, then F of Y is 0. And if F of Y is 0, then P of T is 0. And I have just found that 0 is a solution. Okay, and it turns out it's true. 0 is a solution. Okay, we know it is because at time goes to infinity, phi of t goes to 0, right? And it's an answer. But that's a really boring answer and it doesn't tell us all the other things we need. So that's sometimes called the trivial solution. Okay. Okay, and we don't care about it. It's neglected. Okay. It's like that, you know, circus peanut in the bottom of your Halloween candy. Okay, you're just gonna let it be there till the end, and then acknowledge that it exists. But really not. If you're my daughter, you're gonna keep it in your top drawer, your sock drawer, till like next Halloween until we make you throw it away. And she's gonna be mad at me. But it's a circus peanut. It's gross. Throw it away. Anyway. Okay. So we got 1 minute left. So what's the other possibility? Well, we could have sine of C equals 0, right? So the other possibility is sine of C equals 0. Well, sine looks like this, right? There are lots of times that sine of C equals 0. It only happens sometimes though. It happens there and there and there and there. So how far spaced apart is that? Pi, 0, pi, 2 pi, etc. Okay, so we can say that when C is equal to n pi, or n is equal to, it's actually 0 plus or minus 1, we'll give it 1, plus or minus 2, on forever, okay, we can have a C equal to n pi, and that will be valid. So our solution is f of y is equal to b sine of Cn y, where n is this. N is equal to 0, plus or minus 1, plus or minus 2, 7. That's our solution for that. Okay? So let me see if there's anything else I should say. We will pick this up. I'll say this because this is kind of important, because I say this B now, what we're going to find out, it depends on n. That's going to kind of make sense, right? Because if this changes, that might change our constant. And look, I ought to be a little careful. C appears over here. Okay, so I have to modify my solution for G. So G of t is equal to A, also with an n, exponential of minus CN squared t. Okay, that's the end of step 4. All right, so next time we'll start on step 5, and we'll probably have a little time to talk about step 5. Okay. Step 5 is the mission. The longest.